Yeah, so I'm going to start with some background on the interval, like beta shift on the unit interval, which is well understood and studied. Then talk about how through the analogy we can define a similar map on the p-Adics, some things that are known about that. Then trying to write its natural extension and extending these to more general maps. So to start, sort of classically, what's a beta shift? You work on the interval, you take a real number that's bigger than 1. So when you multiply, initially you get outside of, well, some of the things are going to land outside of the unit interval, and then you take the fractional part to come back in. And this transformation is connected to number theory because you can use it to write out beta expansions, expand your numbers with a base of this beta, and you can take your iterates. This is the k minus first. You take your x, you plug it in k minus 1 times, multiply it by a b, and then take the integer part. So these will all be integers up here. And so just to work with some examples to get a feel for how these types of things work, we could look at what happens when our beta is 2 and look at what happens when x is a third. Maybe let's pick a color maybe different from black for drawing on here. So what happens when you plug in a third? That's going to be approximately here, and you plug it in, and if I can draw straight enough lines, this should end up at 2/3. Right, so when you do your beta x, you get 2/3, and that, so remember our formula, we take the integer part of beta times for d1, this would be beta times t to the 0, so you take that to just be the identity map, and so you get no integer part, and your first iterate is just that fraction. And so then you can plug that 2/3 in. And if I can draw straight enough lines, what happens when we multiply our beta times this then to get our next digit? So that's a 2 times a 2/3 is a 4/3, which is just 1 plus a third. And so our next digit, take the integer part is the 1, and our transformation, the next iterate, is going to be the fractional piece. Okay, and notice we're back at 1/3, so this is just going to bounce back and forth between these 2 points, give us 0, 1, 0, 1, 0, 1. So we can write out our sum from k equals 1 to infinity of the d sub k over beta to the k looks like what? It looks like 0 over 2 plus 1 over 2 squared plus 0 over 2 to the third plus 1 over 2 to the fourth, and so on. And if you're like me and get sick of writing powers of 2 on the bottom and want to just consider that to be understood, we could write this kind of like we'd write a decimal expansion. And what have we got? We've got the 0 and the 1 and the 0 and the 1, and it keeps going. If you want to maybe write a dot for where we start and then draw a line over it to say we're repeating that over and over again. Again, getting the idea that we can just write these coefficients as a string of integers if we wanted to, if that's all we wanted to keep track of. All right, as another example, we could take a beta that's not an integer. So here we've got an algebraic number that's irrational. And if, again, we take our x to be a third, what kind of things are we going to see? So where's our third? Approximately there. We get about 0.61. So they're a bit. So our beta times a third is approximately, I'm not keeping all the digits. And so again, we don't have any integer part, but our transformation applied to a third is going to be approximately this, and then we can multiply again. And we're going to get something that's approximately 1.1277. And so again, our integer part becomes our digit, and our transformation, the next iterate, is from our fractional part. And so that would be 2, yeah, about there. And we can keep going, right? Because it's looked the same so far, except notice we didn't get back to a third. So if we go again, we get something that's approximately 0.2348. And so our next digit is a 0. And our third iterate is this number. And it keeps going. So again, we can take these digits and write this as 0 over 2 plus 1 over 2 squared plus 0 over 2 to the third. And if you get the next digit, it's actually a 0 over 2 to the fourth, and so on. And instead of, again, it's a long thing, I don't want to write out all those powers, but if we keep to the notation where I can use bars over my numbers to say that I am repeating these, you get this long 13-digit string that repeats over and over and over again. All right, so hopefully that was helpful in understanding what these transformations are, what they do to points, where we get expansions from, what those expansions look like to some extent. Here are some properties. I'm not going to give formal definitions for everything here, maybe just more of an idea of what they mean. So we definitely have a break into whether beta is an integer versus not an integer. So when you're an integer, you're going to have these slopes that are starting from your 0, 0 corner, and they end at your 1, 1 corner exactly. And you have as many branches as you've got the size of your integer. That's going to preserve your Lebesgue measure. And when I talk about measures in this talk today, we'll just assume that I'm talking about the Borel sigma algebra. So the one generated by your open sets. And your transformation is isomorphic to your one-sided shift on the same number of symbols as your integer. Okay, so just the isomorphism is going to come from our expansions, right? You take your list of digits that you got from your expansion, and that gives you a one-sided product space in where each coordinate, your options are your digits, and the transformation is shifted over. And this is a measure theoretic isomorphism where we're allowed to throw away sets of measure 0. All right, if you're not an integer, then what happens? You don't preserve Lebesgue measure. So again, what's the idea with Lebesgue measure? Ooh, went too far, one too far. Again, you have to be careful for sets that go over a half or are large, but just to give you a picture of what's going on, if you have sort of a small set over here and you look at its preimage, you're going to get in the preimage 2 sets with half the length That's not a proof, but that's pretty much the idea you have in mind when you're going through a proof that this thing preserves Lebesgue measure. But when you do beta is not an integer, you're going to have this little gap up here. So for example, if you took a little interval up here, it's going to have a preimage of something that is smaller. And you don't get anything from this branch, for example. So we don't end up preserving Lebesgue measure when you're not an integer, but you do preserve something that is absolutely continuous to Lebesgue measure. So they have the same sets of measure 0, which is a nice thing, like the next best thing to preserving Lebesgue measure. And so we talk about something that's isomorphic to these one-sided shifts as being a Bernoulli shift. It's kind of the strongest idea you can have of your iterates being independent. And this weakly Bernoulli is just a weaker notion of independence. I don't want to get into it too much, but you can think of it that way, that things in the distant future and distant past are approximately independent. It's not as strong as this, but it's another independence idea.
Is there,
Sorry, can you say that louder?
is there any notion of shift? I mean, I know it's a crazy question, but on beta symbol, with beta not being an integer, that would make sense so that t beta is kind of conjugate to
Yeah,
what
sure.
conjugate.
So I think the main issue here is you're going to be you're having, how can I say this? The whole space, all of your possibilities of if we're with 2 zeros and 1s, right?
Mhm.
And here, what would we want to look at? We'd still have our coefficients are 0s and 1s. And if we shift the coefficients over, is that still going to be a thing? Oh, I should have thought about that before. That might be the issue if this thing is causing us to lose some of the shifts, or it might be that just part of that space isn't being reached.
Mm. It's related to the fact that it doesn't preserve Lebesgue measure.
Yeah.
Thank you.
All right. And then entropy, again, is a long definition, but it's sort of a measure of randomness. And in both of these cases, your entropy is log of beta, using whichever log you decide to use in your definition of entropy. All right, so these are pretty well understood, pretty classical things. And I probably don't need to define the p-adic numbers for this audience, but I want to, at least on this slide, give a idea of how are we making an analogy between our interval and our real line and the p-adic integers with the p-adic numbers. So our p-adic integers are going to play our role like the unit interval. And just like the unit interval, you can tile the real line with copies of the interval shifted by some integer. You can tile your p-adic numbers with copies of these p-adic integers shifted by some fractional piece. And we can split our p-adic numbers into, if we have any negative powers of p, that'll be our fractional part. If we don't, just take that to be an empty sum as 0. And then the non-negative powers are your integer part, in other words, the piece that's in the p-adic integers. And so just like how did we define our beta shift for our interval? We took something that was going to take us outside of our interval. So we're taking something in the p-adic numbers that has absolute value bigger than 1. So that's going to take us outside of our p-adic integers. And then we come back, but to come back in the p-adic case, we have to come back with the integer part. And just like with our interval situation, we can write out expansions with a base of beta. And how do we find our digits? You again take your k minus first iterate, multiply by the beta, and again, instead of the integer part in the interval case, which was telling you how, like, which of the tiles you were in before you came back, this is the fractional part, tells you which of the p-adic tiles you were in before you came back. Okay, so let's try this with some examples. So again, let's keep it simple, something that has absolute value. I guess I probably could have put 2's here. I meant to. I guess I missed those p's. Let's put that here, p equals 2 for this example. Then 1/2 will have p-adic absolute value 2 is bigger than 1. And let's just, for the sake of keeping things consistent, let's look again at x equals 1/3. Where does that go? What is its expansion? Well, if we're going to work with this in the p-adic case, we probably might like to know what it looks like as a p-adic integer. So it looks like 1 plus 2 plus 0 times 2 squared plus 1 times 2 cubed, no 2 to the 4th, 2 to the 5th, and so on. So after this initial 1, you get the 1, 0, 1, 0, 1, 0 periodic. And then our beta is 1/2, and so beta times x looks like what? We're going to, this is really easy to do by hand, 1/2 plus 1 plus, I'll drop the 0 terms, 2 squared plus 2 to the 4th. Let's just throw one more on here, 2 to the 6th, and so on. And so what do we get? Our first digit. Now our digits look like fractions, which is a little weird. But there you go. So that's our first digit. And our first iterate is going to be the integer part. So the 1 plus the 2 squared plus the 2 to the 4th, and so on. And then we can, for the next digit, multiply that by beta again, which is 1/2, which is really easy. It's 1/2 plus 2 plus 2 to the 3rd plus 2 to the 5th, and so on. Okay, so our next digit is 1/2, and our next iterate is the rest of this. And if I move this just a bit, if we look one more time, multiply that by 1/2 again, we get a 1 plus a squared plus a 2 to the 4th, and this is repeating, so the next one will be a 2 to the 6th. Our next digit, there's no fractional part, so that's a 0. And our next iterate of 1/3 is just going to be all of that. And notice that should hopefully look familiar. And so we're ending up in a cycle again between these two. So what does our expansion look like? It looks like we've got, so again, we're doing sum of k equals 1 to infinity of d sub k over beta to the k. And so we have the 1/2 over our beta is 1/2 to the 1st plus 1/2 over 1/2 squared plus 1/2 over, sorry, there's a 0, over 1/2 cubed plus, then it repeats, so a half over 1/2 to the fourth and a 0 over 1/2 to the fifth and so on. And if you multiply everything out, you get a 1 plus a 2 plus no squared plus 2 to the third plus, and it's going to repeat, so 2 to the fifth, and so on, which hopefully looks like what we started with. All right, so the 1/2 is particularly simple. And again, if we drop the powers and just look at the coefficients, what were our coefficients here? It was a 1, 1, 0, 1, 0, 1, and so on. And then after our next iterate, it was a 1, 1, 0. Sorry. Nope, that's wrong. There we go. 1, 0, 1, 0, 1, 0, 1. Okay. And the next iterate would be a 0, 1, 0, 1, 0, 1, and so on. And so we can see what is this doing if we just look at the coordinates, this multiplying 1/2 and taking the integer part is just shifting our coordinates over, which is maybe why it's not super surprising that it was really easy to see we got the same thing back out. All right, let's try this with a non-integer because that's a bit more interesting perhaps. So we've got, again, algebraic, irrational number in our p-adic. And again, sorry, I should have changed these p's. This p is 2 still, if it wasn't obvious from the partial expansion of what beta looks like. So we've got a root that at least starts like this. And again, keep things consistent. Our x that we'll look at for our example will be a third. And so what happens when we do beta times x, we get, maybe I'll do this. I think we get the idea. The fractional part when we multiply by beta gives our first digit, which is a half. And the integer part gives us our, that should be a 3. There we go. Our image under our transformation, which in this case is approximately 1, 2, 2 cubed, 2 to the fourth, and so on. And then if we take this now, and again, we're going to multiply by beta, our fractional part becomes our digit, and the integer part becomes the next iterate, which in this case is, where am I on my page? Sure I wrote that one right. Okay. 1 plus 2 plus 2 to the fourth plus 2 to the fifth plus 2 to the sixth, and so on. And again, if we multiply that by beta, it splits into our digit, which is a half, and our next iterate, which is 1 plus 2 squared plus 2 to the third plus a lot of zeros before it picks up a few more digits, and so on. And if you keep going with this, so again, if we like to write this as sort of our decimal notation, even though if you'll allow me to write fractions in a decimal notation. What do our digits look like? We have a half, and then our 1/2 zeros are repeating. And here, if we do a similar sort of writing this down, we're going to get something like a half, a half, a half, and then the repeating part is a half, 0, 0, a half, 0, a half, 0, like that. And you can do, write it out with betas, take a geometric series to sort of compact this down to a fraction, and then use your properties of the fact that beta satisfies this equation to show that, in fact, we've kept track of our digits correctly. You get a third from this expansion. All right, so it's a little weird to think about having a digit that's a fraction, but this is what we're doing here. And again, in general, for any prime p, if you take your beta to be a 1 over p, what happens? You multiply it through. That first coordinate ends up being the fractional part that you drop when you take the integer part. And so everything, all your coordinates have just shifted over. We'll write this transformation where you just shift all your coordinates over by a sigma. That's a pretty standard notation for a shift in dynamics. And so if you multiply, if your beta is 1 over p to the n, that's just going to shift over n of your coordinates at once. And so that's the nth iterate of your shift. And you can even, if you have an arbitrary beta, what's its size? It's going to be some p to the n that's bigger than 1. You can write that beta as something that's a p-adic integer with absolute value 1 over the p to the n. And what you really have, you have this nth iterate of the shift multiplied by your multiplication by b. And just to give us a hint of where we're going later, multiplying by a b when your b has p-adic absolute value 1 is an isometry. It doesn't change your distances. The shift does, the multiplication by b does not. Okay. So hopefully with some examples, we get a feeling for how these are working, how we can think about them in terms of other maps. And they've been studied before. So again, a reminder that our beta should be bigger than 1 in absolute value. I think D'Ambrose and others, the co-authors in 2000, might have not required that restriction, in which case you have to put some other conditions on things like making this a log plus. But your topological entropy is going to, just like your interval, be log of beta, except now we're taking the p-adic absolute value before we take the log. Kind of like the integer beta shift, your p-adic shift is going to preserve Haar measure, which is what you should think of as the analog of Lebesgue measure. It's the translation invariant measure on your space. And it's ergodic. So we don't have a split here in terms of is our beta an integer versus not an integer, because we don't get that kind of split of behavior. Each of your small balls does cover a larger ball. It doesn't have this sort of partially covering property that you saw when your beta in the interval case was not an integer. That kind of behavior doesn't occur here. Okay, so Kingsbury and co-authors in 2011 showed that again, the only reason we're saying this is equal to p to the n, it is to some p to the n, which one? That one. That tells you which shift you are topologically and measurably isomorphic to. And then, and here they didn't call it a beta shift, but it has the same formula. It was one of their examples in their paper. And then Scheicher and co-authors in 2015, they connect your properties of the beta to the properties of points that have finite or periodic beta expansion. So again, it's well known in the interval case what you need for beta so that your rational numbers and the rationals with the beta have periodic expansions. And this is doing the similar sort of question, but for your beta expansions. When are you going to get, for example, your rational numbers all having a finite or periodic beta expansion?
Are you allowing beta to be non-integer?
Yes. Okay. And so one thing that is used to study the interval beta expansions are natural extensions. So I wanted to see if we could have a similar analogous natural extension for our p-Adic beta expansions. By the time I ran down all of the references I found, it seemed like we knew a lot about it anyway, but just kind of some warm up for I'd like to look at other transformations that are related to other expansions. It's a good practice before looking at other things that aren't studied as much. So a natural extension, what's the idea? Here's the long definition, but the idea is invertible things can be easier to study than non-invertible things. So we have our non-invertible thing. We want a bigger system that's invertible that contains it, and ideally the smallest one. Okay, so our X is our bigger system, our Y is our smaller system, then our X is going to be the invertible one and the Y is the non-invertible one. This map you can think of acting as kind of like a projection map. In all of the examples in this talk, it will be a projection map. This is just making sure our sigma algebras are going all right with each other. This is semi-conjugating so we can relate our maps to each other. And then, of course, we also want our measures to agree nicely. And so again, we have that X has Y as a factor. So our invertible system is containing, I mean, Y could be invertible, but then its natural extension is just going to be itself. That'd be boring. This looks like a complicated condition, but the thing you want and what results from this is just that this is the smallest invertible system that contains your Y. Anything else that's invertible that has Y as a factor is going to also have X as a factor. Okay, so it looks complicated, it sounds complicated. Here's some examples that are probably not so bad to follow. So again, Dejani and co-authors, lots of co-authors in these papers in 1996 gave this formula for natural extensions for beta shifts. I don't know that they did all betas, but at least like some of the, yeah, it's been a while since I looked at that paper. I don't remember if they needed it to be algebraic to put this thing together, but a good number of betas to get a nice natural extension. And it's not so bad when your beta is 2, which was the first example we looked at. So instead of looking at the interval, our bigger space is, because remember, we can make our space bigger, is going to be the interval cross the interval. And just to give you a feel for what's going on, what are we doing? Think about the partition into these two pieces. What happens to those two pieces? In your x coordinate, what happens? Things stretch because you've got your beta shift. And then this piece in the y coordinate here, we're keeping track of our digits essentially, right? This had a first digit of 0. Everything here is going to give you your next digit of 1. And so your x is keeping track of your transformation, your y sort of keeping track of your digits. So you can go backwards if you need to. That's where our invertibility is coming from. And so when beta is not an integer, your space is not the whole square anymore. It's not the whole unit interval cross unit interval. In this particular example, you've got these sort of 3 pieces in your space. And what happens to this one piece? It gets stretched. And then everything in here is going to give you a digit of 0. And these 2 pieces, again, get stretched. And notice this was not an integer. It didn't go all the way. This piece doesn't make it all the way to the end either. But these two will both give you a digit of 1, and they are both up here. So again, the idea is your horizontal is keeping track of your transformation. Your vertical is keeping track of those digits that were popping off, right? So you can go backwards to figure out where you came from. All right. So again, you can take the analogy and the exact same formula after you interpret it analogously works. Your transformation is in the x coordinate, but instead of the fractional part, you take the integer part because you want the thing that brings you back to your integers. And instead of the integer part there, you take the fractional part because you want the thing that keeps track of those digits, right? So that you can go backwards. And then the inverse you can write in this formula. And to show that these are actually inverses of each other, kind of the key idea, and let me kind of, if we think of this as u and this as v, right, that we're trying to go backwards with, these two things have the same fractional part. So what is beta times v? It's going to be u divided by beta, so it's the fractional part of beta x plus y, and this y is a p-adic integer, right? So what's the fractional thing of this going to be? You're going to drop your integer part, and it's just the same as your fractional part of x. That's really the key idea when you're trying to go through these formulas, plugging one into the other to show that you get back to your original coordinates. That's mostly what you're using. All right. And so again, what's the picture of what's going on if you're thinking on Z2? Now, again, don't take the line too seriously, literally. Think of this as the ball in Z2 that starts of things that start with zeros. And this is the ball in Z2 of things that start with ones. And vertically, same idea, ball of things that start with zeros, ball of things that start with ones. This x coordinate, again, it stretches things out, is going to keep track of your transformation, your shift. And the y coordinate is keeping track of your digits so that you could go backwards, those digits that were popping off, so you can put them back on. Okay. But unlike, and this maybe shouldn't have been a surprise after we talked about it preserving Haar measure before, unlike the interval case, when you have something that's not 1 over 2 to a power, 1 over p to a power, you don't have to make this smaller. You still have your whole zp times zp, and it works. Same formula, works just the same on the whole space. Okay, So what other maps can we look at? So alpha beta shifts on the interval, you take your beta x, but then you add an alpha before you take the fractional part. And so what does that do? That gives you a little gap on the left and a gap on the right. And so that makes things a little bit more complicated. And so these are not quite as well studied as just the beta shifts. But when you look at p-adic alpha beta shifts, what can you do? You can do a very similar thing to how we broke down that beta shift before. You can express this transformation, find an a and a b in your p-adic integers. Your b is going to have absolute value 1. And then this transformation is just your linear thing and then shifted. And so again, we want to keep things close enough together so that the shift doesn't, we can still keep track of things after we shift n times. But if we start within 1 over p to the n, well, what can we do here? Well, that shift is p to the n just in the size of the distance between the insides. And then you can, okay, the a's cancel, you've got the b's. It's still in isometry. This affine bit is still in isometry when your beta has absolute value 1. So you still have this scaling, which has a name. We very often look at p to the minus n, p to the n locally scaling maps. And you can put different numbers here and here for these scalings, but this is all that I'm going to look at in this talk, is when you've got p to the minus n, p to the n. So the p to the minus n is how close your x and the y need to be to each other. The p to the n, that's the constant that you get scaled by your transformation. And again, in this 2011 paper, they showed that not just that beta shift, but all these locally scaling maps, p to the minus n, p to the n locally scaling maps, are topologically and measurably isomorphic to your nth power of your shift. And so that tells us what? That we showed that this alpha beta shift was p to the minus n, p to the n locally scaling. So it is isomorphic, measure theoretically or topologically, whichever you wish, to your nth iterate of your shift. All right, can we push this farther? So to be able to write a more general natural extension, I wanted to be able to write any of these p to the minus n, p to the n locally scaling maps as an iterate of a shift composed with an isometry, because that makes things nice and easy to work with. And it's not that hard to do. What do you take for your isometry? Well, shift your transformation down to make some room for some digits that are keeping track of the digits at the beginning to keep you 1-to-1. And so this isometry will be invertible. There are probably, I'm sure, lots of other isometries you could take, but this is the one I used in the proof. It's easy to work with. And once you have this isometry, you can show that you can use it to write a natural extension. It looks kind of complicated when you write all this out, but the idea is still the same. This is just your transformation. And this part is just keeping track of the things you've lost from your shifting. Okay, and if we take that proof or that f that I showed you above and pull it through these things, it's not easy to write what the inverse is going to look like, but otherwise, what do we have? We have our transformation. We are pushing down our y's so that we can make some space for some digits, and then we keep track of some extra digits, and we need that inverse of the isometry, but otherwise, it's not so bad. All right. Where are we? All right. So all of these p to the minus n, p to the n locally scaling maps seem to work very similar. They're all isomorphic to this nth iterate of the shift. So very often these p-adic things, when you try and do a direct analog of the real thing, it becomes a bit simpler. This is another situation where that has happened. But there are ways to tell some things apart. So remember, I've been writing coefficients over and over and over again to give you an idea that we can think of these things as a product space by just looking at what the coefficients are of our p-adic integers. And so on our p-adic integers, we can put other measures where we put different weights instead of 1 over p, 1 over p, 1 over p, which would give you your har measure. You could put different weights for the different digits. And so I showed back in my thesis that for multiplication, which was part of our definition of this, well, we can incorporate it into our definition of our shift, that, all right, if you've got multiplication by -1, you have some symmetry. Some of these will be non-singular. But otherwise, if you have a rational number that's not 1, which would be boring, it's just the identity, or -1, which has some symmetry you can deal with. I think that's supposed to be, oh, yes, okay. So the only product measure this is non-singular for is the har measure that it preserves. Does it preserve? Yes, okay. Otherwise, you get a singular transformation for any of these other product measures. And so, again, you can bring this into your, sorry, I copied this from a paper and I missed these T's. These should be S's for our p-adic ones. If you're 1 over p to the n, you're preserving your any of these measures. If you're negative 1 over p to the n, you can only preserve the ones that are palindromes, and, well, our measure would be a palindrome. Those are the only ones that are going to give you something that's non-singular. And then if your b here is any integer that's not plus or minus 1, then you're not going to be non-singular for any of those except for the har measure, which you should expect. All right, so I hope that was a slow and easy talk for the end of the day with lots of examples. Do we have any questions?
Absolutely. Thank you for that. It was nice actually to see some of the calculations and see some of these things done by hand. I do have one quick question before I let other people ask. You said this thing about, even on this last slide, with a negative 1 over p to the n, that only when you have a palindromic probability vector.
Mm-hmm.
Can you explain just a little bit more what that means?
Oh, sorry. Just your vector that's giving you your weights should be a palindrome as numbers, right? So.
Oh, okay. All right. Fair enough. That is an easy way. Okay. Yes. Thank you.
Sorry, that wasn't, yeah, I don't think I put that definition anywhere.
It totally makes sense. Yeah, in retrospect. Questions from the audience?
It must be odd then, or for this to be defined, right?
Sorry?
P must be odd then. It must be an odd prime, right?
P, yes.
Because otherwise you cannot talk about palindrome. Right?
Yeah.
Okay. So your product measures in the last two theorems are Bernoulli measures, right?
Mm-hmm.
Yes. Yeah. But with not equal weights.
Right, exactly.
Mm-hmm.
Could you talk about something being a palindrome if it's like?
I don't know. I mean, my impression, but maybe that's just a question of convention, I guess.
Like, is a palindrome?
I don't know. Yeah, I put a mirror in the middle, but maybe
Right.
maybe if you if you take that as a, and yeah, then you probably can allow p equals 2. Yeah. Mhm. But could you give an idea, intuition of why the palindromic condition is necessary and sufficient for
Yeah, so see if I
singularity,
can remember exactly.
or just the intuition? I mean,
There's some relationship between the multiplication and the addition map when you're working with -1. And oh, can I remember exactly how that went? Like, it's not what I want. If you put like x plus 1 and subtract that, you get minus x minus 1. And so this is what a multiplication by -1 composed with a translation. Let's just do a +1 map is the multiplication by -1 composed with a, no, adding minus.
Mhm.
That it's something like that where you can kind of relate it to an addition.
I see.
Um,
Hmm.
where, man, I'm sorry, it's been too long.
All right. Any other questions for Joanna? Well, if not, let's thank the speaker again for an excellent talk. It was wonderful. Thank you to all the speakers tonight, and again to the organizers who managed to pull this thing together. We will see you again tomorrow morning at 9 o'clock my time. That is approximately 17 hours and 8 minutes from now, if you want to know what it is in your time. But see you again tomorrow morning. Thank you, everybody, for sticking it through to the end of the day. We will get these things up and visible so that people who are asleep right now can see this part of the conference. So thank you again, everybody, and we'll see you tomorrow morning, or
Goodbye.
whatever time it is where you are. Okay. I'll stop the recording.